So now we've got the double slit experiment set up for Thelma and Louise. So there's a laser, passes through two slits and you get bright bands and dark bands. Obviously the white ones are bright, the dark ones are the dark bands. So this is the double slit experiment. Before doing the experiment, Louise believes that the central band, the one directly opposite the centre point, is a dark band. Thelma believes it's a bright band. Who is correct? Outline your reasoning. So the centre band, if we had our two slits, I'm looking down on them now, here's one slit, and here's the other slit. And the central band is right in the middle. The distance from there, I'll get rid of that. Yeah, I'll try that again. The distance in another colour, the distance from here and the distance from here to that slit. My rulers are a bit wonky, but it's the same distance. They are the same size. Because those distances are the same, that's what we say the path difference equals 0. Because it's in the middle, distance from one slit to the middle and distance from the other slit to the middle are the same, therefore path distance is 0. That's going to be really important when we do our explanation. Alright. So the path difference, let's write about path difference. And from now on I'm just going to refer to that as PD. To centre of screen equals 0. Therefore, waves, which when the waves go through here, because they're from a laser, they start off in phase, they start off lined up. So therefore waves which start in phase, go same distance, and because they end in phase, they add together. That's called constructive interference. Constructive interference occurs. Therefore, it's a bright spot. Who was saying the bright spot? Louise believes it's going to be a dark spot. Thelma believes it's a bright spot. Thelma is correct. Alright, precision measurement shows that the path difference in the middle of dark band A, here, is greater than the path difference in the middle of the dark band B by 496. From this information, determine the wavelength of the laser. You may include a diagram. Right. The path difference between bright bands, this one could be the middle, so that'd be 0 wavelength. The next bright band's 1 wavelength, 2 wavelengths, 3 wavelengths. The dark bands are half, 1.5, 2.5 wavelengths. So between two dark bands, the difference in path differences, because that's what it is, a bit confusing, but they're saying one is greater than the other. So the difference in path differences for adjacent, same coloured bands is 1 wavelength, because that could be a half, 1.5, 2. So the difference between 1.5 and 2.5 is 1. So let's write that down. Difference in path differences of two bands of same, let's just say colour. No, let's not say colour, let's say darkness, which are beside each other, is equal to 1 wavelength. So therefore, 1 wavelength, and I've said that equals 496. So 1 wavelength equals 496 nanometers. So that's your answer for that one.